And hello, everyone. So we are here today to talk about plate tectonics. Plate tectonics is really, the great unifying theory of geology. Without plate tectonics, nothing makes sense, right? Plate tectonics takes all those things that we know about geology and helps us to actually understand them. Without plate tectonics, geology kind of collapses into this pile of things that we know but that we don't understand, right? It's sort of like evolution for biology and paleontology that way, right? It gets all these things that we know and ties them together and gets them to make sense. Now, interestingly, plate tectonics is not a very old idea. Geology as a science really kind of got its beginnings in the mid 1800s. Um, and plate tectonics was, I don't know, 1950s, 1960s, 1970s, and kind of still ongoing, really. So geology, labored for, about 100 years without any great unifying idea to get all this stuff that we were learning to actually makes sense. And so it's a very important idea. You've probably heard lectures on it in maybe oceanography classes, or you've probably heard people talk about this before. But let's make sure we hit it again. Let's make sure we get it right. So the story of plate tectonics begins with another idea, and that idea is continental drift. Now, you might have learned that these are the same thing. They're kind of not. And so, yeah, and as I look at this slide, it occurs to me, I don't actually see where my little picture is on this slide as I'm talking. So I might be kind of covering over that picture. If I am, I'm sorry for covering Alfred Wegener's picture. But anyway, continental drift is a different idea. There's a few different ways of thinking about the relationship between continental drift and plate tectonics, and we'll talk about those. But for now, let's think about continental drift as an older idea that in the end kind of didn't work all that well. And so, but look, in 1915, Alfred Wegener, a German meteorologist, not a geologist. That's actually going to be important. He was an Arctic meteorologist. He studied the meteorology of the North and South Pole and extreme North and South regions in general. But he kind of put forward this idea that he thought that the continents are moving, and he published his book in 1915. And you've all grown up in the 20th century, 20th and 21st century, where we just kind of know the continents are moving, right? I tell you the continents are moving. That's not that big a deal. But in 1915, it was a big deal. It was a very big deal. So what led Alfred Wegener to think this? Well, a few things. First of all, we were getting really good maps, right? Have you ever looked at a map drawn in the 1400s? They didn't know where anything was, right? By the early 20th century, even before then, we were getting pretty good maps. And when you do that, you realize, when you look at a pretty good map, you realize that the continents fit together. Right? And maybe most easy to see is how South America and Africa really kind of want to spoon up against each other. By the way, Florida goes down in that notch right there. And in fact, we can reconstruct everything back into one giant supercontinent that Alfred Wegener called Pangea, a word you've probably heard before. That's Alfred Wegener's word. Where all the continents were, back together at the same place. And here's a little bit better drawing of it, and you can see that. You can see that notch there where Florida is kind of stuck down in there. Florida had been riding along on a tectonic plate with Africa, by the way, until Pangea came together. And then when it broke apart in such a way that that Florida and the southeastern United States went with North America, and I'll show you that probably in the next lecture. My idea here is to talk for about an hour, between an hour and an hour and 15 minutes, which is the time that I would normally have in class. to do this, and we will take a break too, by the way. So anyway, so continents seem to fit together. Now there was another idea at the same time called the expanding Earth theory, right? Which is the idea that the Earth is getting bigger. And that would kind of account for the continents fitting together, right? Because their idea was that, and I think you can see my hands, was that, if the Earth, gets bigger like a balloon, continents that were once against each other are going to break apart as the Earth gets bigger. No one was really sure how or why it was getting bigger. They just thought that maybe it was. And so that was the kind of thing that Wegener was having to deal with, was these water, very important. Where this idea that the Earth was getting bigger. Another line of evidence that Wegener used, and is interesting to this day, and that is that fossils, if they are old enough, will cross from one continent to another in really kind of strange ways. For example, here we've got this Lystrosaurus here. Lived here in South America, but then also over here in southern Africa. That's okay, but not terribly unusual. But it gets better. This freshwater reptile, Mesosaurus, lived here in South America and also over here in Africa. Still not too weird, but it's going to get weirder. We got this glyptodont, which my arrow is in the wrong place, so ignore that little arrow. This glyptodont, though, lived here in Africa. It's the little speckled thing. Here in Africa, down here to Madagascar, up here to India, and then down here into Antarctica. Now that starts getting weird, right? Things don't live in northern India and Antarctica. Right? Those are very, very different environments. Much less, Eastern Africa and northern Madagascar. Right? That's just odd. Okay, but then the fossils that really kind of take the cake for this is something called the Glossopteris flora, and this is a swamp. It's a bunch of fossils. It's a bunch of different plant fossils, dominated by a fossil named Glossopteris. We find the Glossopteris flora in South America, across Africa, southern Madagascar, southern India, Antarctica, and central Australia. Okay, things don't live in all of the right, things don't live. Those are very, very different environments, right? Things just don't live in environments that are that separate, right? And if we look, if we take the pictures away and we just look at these distributions, they don't really seem to make a whole lot of sense. But watch what happens if I do that. Right? If I bring the continents back together to make a giant southern supercolony called Gondwana, we can see that the Mesosaurus range makes sense. The Lystrosaurus, the Glossopteris range is just a giant inland swamp, basically, and we live in Florida. We know all about giant inland swamps, and so this all makes sense, but it only really makes sense if you bring the continents back together. These fossils, by the way, are pretty old, and by pretty old, I mean older than the dinosaurs, or let's say the non-avian dinosaurs. The dinosaurs were around for the breakup of Pangea, and so these are even older than that. So if you look at really old fossils, they cross continents. If you look at really old rocks, they cross continents too. The rocks that make up our Appalachian Mountains here, someone is blowing leaves or something outside my window, by the way, so if there's weird background noise, that's what it is. The Appalachian Mountains up here extend over here into the mountains of the British Isles, including the mountains of Scotland, and then the Caledonian Mountains up in here in Scandinavia. And in fact, they also extend over here to Africa. And in fact, if you drill underneath all this limestone in Florida, you'll hit rock that is the same as this rock over here in Africa. And I don't mean, there's, a coal here and a coal here. No, no, no. The same coal, overlain by the same shale, underlain by the same limestone or something. You have exactly the same rocks. Now, the landscapes are very different, right? This has all been glaciated, and, the landscapes are very different, but look at the rock. When you look at the rock, it's the same. And the reason it's the same, right, is because of this. Right? When Pangea came together, we ended up throwing up what we today call the Appalachian Mountains. That mountain range, which was then called the Central Pangean Mountains, extends over here into Africa and all the way up here into Greenland and Scandinavia and, all those places we saw on that map, right? When Pangea breaks apart, all those rocks end up on separate continents. And so once you start doing geology on different continents, you start to notice, these not similarities, these identical rocks on different continents. And so, that provided pretty strong evidence. There was also some really interesting evidence from what we might call paleoclimatology, which is just, studying the Earth's ancient climate. And there are some rocks that are very, very indicative of climate, and coal is one of these rocks. Coals form in swamps, right? They're okay. See, coal is like my thing, or the ecology of coal swamps is like my thing. So I'm really having to restrain myself here. But anyway, coal forms in, let's just say, in the tropics. Right, and so you need warm conditions, you need wet conditions. Coal is a tropical deposit, and yet look at where these coal beds are. Right, North America, they're up here. I mean, just think about where in North America we mine coal these days. Right, places like Pennsylvania, West Virginia, Kentucky. Right, these are not tropical regions, right? They don't look like that. Okay, there's a really good reconstruction by Bill DeMichael of the Smithsonian Institution of what one of these coal swamps would look like. And they're tropical, right? You don't see coals, up here, right? In Pennsylvania, that swamp that made that rock should not exist this far from the equator. So that's a little bit strange. And I'm going to pause the video for 1 second and deal with something. I will be right back. Okay, so we have coal deposits in places where the swamps that form them simply should not be. What else? Well, glaciers. These white bits on the map are glaciers. Glaciers are sheets of ice that flow. Let me show you. So let me get out of here. Let's see. Let me get out of here. And there we go. And let me show you what glaciers look like. So here's Google Earth, and let's have a look. So let's go over here to Alaska. I am nowhere near Alaska. There we go. Sorry, I'm not used to dealing with it in a window that is actually rather small, but that's okay. So if I look here, we can see, these rivers, if you will, of ice flowing down out of the mountains, right? Glaciers are what you get when you have more snow falling in the winter than you have melting in the summer. And so the snow packs into ice, and then that ice flows, okay? And so we can see a glacier coming down here. Here's another glacier coming down here. Here's one coming down through here, right? And these are all sourced up here in these mountains. And you'll notice, though, if we look at this, you see an awful lot of glacially carved valley without any glacier in it, right? We are losing glaciers at a prodigious rate. As we burn fossil fuels, release carbon dioxide, and warm the planet, this ice is melting back. And this ice keeps our planet cool. We will talk about that at some point, but so as you melt back ice, the Earth gets warmer, which makes the ice melt back more, which makes the Earth warmer, and you can see how that's going. But these are glaciers. They flow. They move. We can also look. Let's find another one real quick. There we go. Greenland. Right, Greenland, great, best advertising in the world. The big island covered with ice is Greenland, and the little island not covered with ice is Iceland. So yeah, but if we look out here at the edge, we can see also that this huge sheet of ice is flowing. Right, we can see these paths where the ice is flowing. Now this is sea ice. That's not glacier. That's sea ice. That's different. And we can also once again see. This glacially carved valley without glacier in it, right? And so, but these big sheets of flowing ice. Now they leave behind a geological record. And let me bring the PowerPoint back. And hold on, I'll make it so y'all can see everything. And I need to do one more thing here. And there we go. And there. So now y'all can see everything again. So I was fortunate enough a couple years ago to travel to British Columbia and look at some glaciers. And so there I hear glacier selfie. Yeah, okay. So there's the glacier without me in it. And so it's this is the Athabasca Glacier in the Columbia ice fields. And once again, let me get some water here. My throat's kind of scratchy. And so yeah, glaciers leave behind a very specific kind of deposit. They have a very, very easy to read geological signature. This is if I'm standing here looking at the glacier, walk back a little bit and turn to the right, and it looks like that. And so this rock here is glacial till. Glaciers pick up rock from all kinds of different places and carry it and then just drop it as they retreat. And so you end up with these piles of rock that are all kind of different from each other. I mean, there's a whole bunch of different kinds of rock right in there, all carried by this glacier. And then if you see the bedrock, and it's difficult to see here, so let me show you here. The bedrock has striations on it. And these are grooves that are carved in the rock by the glaciers. There's a closer up picture of them. And someone who knows a bit more than I do can look at this and actually tell you which direction the glacier is moving. Okay, now it's pretty easy for us. It's either that way or that way, right? And considering that the glacier is right over there, that's not hard to figure out. But if this was an ancient glacier, you don't have the ice there anymore, but you can use the glacial till to figure out that there used to be glaciers there, and then look carefully for some striations, and you can tell what direction the glacier is moving. So we have records of glaciers from millions and millions and hundreds of millions of years ago, and when you look at them, they don't really make any sense, right? Glaciers flow downhill, like everything is going to flow downhill, right? And so it makes no sense here to have glaciers coming up out of the Indian Ocean into the tallest mountain range in the world, the Himalayas, right? They should be going the other way, right? Or here coming out of the Pacific Ocean up into the second tallest mountain range in the world, the Andes, right? That makes no sense. Coming up out of the water into Central Australia, here, look, here's a glacier here on the equator, right? Unless it's on a very tall mountain, you don't really get glaciers on the equator. You really just don't. And the direction of motion doesn't really make any sense. And, right, this just doesn't make any sense, right? And, we know they're there. We know they were there. And we know what direction they were moving. And it just makes no sense. So we got two things. We've got coal seams where they ought not be, really far from the tropics. And then we got glaciers moving in ways that simply do not make any sense, right? Well, you see this coming. What if I do that? right? What if I bring all that back together? Well, notice that puts our coal beds right on the equator where they should be, right? And then South America, Africa, India, and Australia are all attached to each other, and sitting pretty near the South Pole. So you get a pulse of continental glacier like Greenland. Moving its way northward, which makes sense, nowhere near the equator. And yeah, right. Look, the Himalayan mountains don't exist yet. India hasn't hit Eurasia yet, so that's fine. The Andes Mountains don't even exist yet. The plate boundary over here that makes all those volcanoes in South America isn't there yet. Isn't doing that yet, and so this makes perfect sense, right? And so all these paleoclimate indicators don't really make any sense like that. But if you bring everything back together into that giant supercontinent Gondwana, a few 100 million years ago, now it all makes sense, right? And so Wegener wrote a book. I think it's called The Origin of Continents. I'm honestly not sure, but he wrote a book, and he laid all this evidence out, right? He says, look, the continents really do fit together. Rock bodies, if they're old enough, cross from one continent to another. Fossils, if they're old enough, cross from one continent to another. These paleoecology or paleoclimate indicators that we have only make sense if you bring continents back together. And he laid out his case. And it really didn't work. People in 1915, people just did not believe him. They were just like, yeah, no, just no, right? That can't be, right? They were not really willing to go there at all. And a lot of it was that, but also Wegener's a great guy. I got no problems with Alfred Wegener, but his idea had a couple issues. Okay, first of all, there was no known mechanism for moving the continents. In other words, Wegener's having to say, hey, I think the continents are moving. And people are like, great, what's moving them? Yeah, I think the continents are moving, right? He had no clue, did not know. So he lacked a mechanism. That was a problem. That really was. Now, remember how in the scientific method lecture I said if you want to hear a physicist stutter, ask them why there's gravity? If you want to hear a geologist stutter, ask them what's moving the tectonic plates, because we're not sure. Now, there's no question that they're moving, right? We've got GPS transponders set in concrete. They're moving, okay? But, in the absence of direct evidence for that motion, the lack of a mechanism is a problem. A much bigger problem than it is today. The other thing was Wegener got something affirmatively wrong. He thought that the continents were moving, but the seafloor wasn't. So now he needs to somehow move, a tectonic, or a continent in his case, somehow, I don't know, over or through. I don't know. I don't know what he was thinking. But one way or another, he's got to get that continent to move and the seafloor to not move, right? And it turns out that the recognition that seafloor is moving too is what's going to turn continental drift into plate tectonics. The other problem is that there were, alternatives that sounded pretty good to the idea that those rocks and fossils are crossing continents because those continents used to be together. People are like, well, look, maybe there's a mountain range, right, that goes under the Atlantic Ocean off the coast of New England and then comes up again in Europe, right? And that's why, I mean, basically, no one knew anything about the ocean, so it was this giant garbage can that people could just throw ideas into, and no one could really say anything because no one really knew what the ocean floor looked like. And I got these little drawings over here, but I suspect that my picture here is covering up some of this. But, rafting, right? The idea that, look, animals get from one continent to another by just clinging on to debris. And all of this stuff happens. Rafting happens, right? Land bridges, Panama is a land bridge between North America and South America, and there have been all kinds of faunal and floral migrations over that land bridge over the years and years and years and thousands and of years. Island stepping stones, right? If you want to go from one continent to another, you might not need to go from one continent to another. You might be able to go to a series of islands in between them. And the one you probably can't see down here for my picture is, yeah, continental drift was in there. But no one really believed it. just no one did. Now these other three things, land bridges or Isthmian links and rafting and island stepping stones, these things actually happen. Biogeographers, understand the importance of these things, and people were then using them to explain that distribution of fossils. And then they just said, look, maybe those rocks go under the ocean and come up again. I don't know. Basically, anything sounded better than the continents are moving, right? They were pretty much willing to believe anything other than that. The other thing, my last bullet point, politics, politics, politics. Yeah, here's the thing, right? Remember I said Wegener was a meteorologist? Yeah, that was a problem. Because he comes out with an idea in the science of geology, and he's a meteorologist. That's not really good, okay, and it should be. That's bad. Okay, that's a bad thing. But geologists and scientists in general are people too, and we don't like other people playing in our sandbox. And so when Wegener comes around and says, "Hey, here's a geology idea that sounds kind of crazy, but it just might be true," all the geologists are like, dude, you don't come to our parties. Who are you? I don't even know you. And they're just, you're a meteor. Don't you have a cloud to go look at? Go look at your cloud. Leave the geology to us. You clearly don't understand the things. And he could not get any backing. He did not have a posse, right? He did not have a bunch of scientists who had his back, who when he came out with this somewhat crazy idea said, yeah, but I think he's right. Look at the evidence, right? Didn't have that. So the idea would die with Alfred Wegener. He would go to on an expedition actually into Greenland, ironically enough, and never come back. So the idea, and when after he was gone, no one was going to stick their neck out for this. They just weren't. Okay, so that was kind of a problem. And like I said, when Alfred Wegener died, the idea kind of died with him. It really did. So let's fast forward from basically from World War I to World War II, right? From 1915 to 1940s, and think about how are we going to get from from continental drift to plate tectonics, right? That's going to require some technology, and understanding the ocean floor is going to be the key here. Okay, because once you understand the seafloor, then it's no longer this sort of garbage can that you can throw ideas into to explain away Wegener's evidence for plate tectonics, right? No, once you actually see what the seafloor looks like, that's going to be the key here. It really is. And so World War II is going to give us a technology to map the seafloor, and that's going to help us understand plate tectonics. And one of the people who was instrumental in this was a geologist named Harry Hess. And at the outbreak of World War II, Harry Hess joins the Navy. He was professor at Princeton, and he took a leave of absence and joined the Navy. And so, since he had a college degree, had a PhD, they made him an officer and they gave him a ship. Now, they're not going to give him an aircraft carrier battle group or something, right? No. They gave him a transport ship, the USS Cape Johnson. Okay, and this was important though because the thing that I think a lot of a lot of Americans don't understand about World War II. World War II did not begin in 1941 when the Japanese bombed Pearl Harbor. Right, that's when America entered the war. World War II had been going on since 1939. Right, with Hitler rolling across Europe and bombing London and all kinds of things. Right, so by the time we came to that particular party, you know, it was late in the game. It really was. And what people needed from us was mostly stuff, right? I mean, they were running out of stuff. And by stuff, I mean everything from, food to whatever. They were just running out of stuff. And so, and plus, right, obviously, World War II was not fought on American soil. So we had to get our military over there, to borrow a phrase from a song. But anyway, and so we started producing these relatively inexpensive transport ships called Liberty ships, and suddenly, we start shipping people and stuff across the Atlantic, across the Pacific, to fight the war. Well, okay, what does this have to do with plate tectonics? Okay, I promise it'll have something to do with plate tectonics. Okay, so the Germans aren't stupid. They realize that our supply lines are stretched really thin all the way across the Atlantic Ocean, right? And so winning the war for them was going to involve one way or another cutting our supply lines. So what do? They build submarines, right? Lots of them. Relatively cheap, relatively inexpensive to build, easy to crank out submarines, right? And they send these, they were called wolf packs, out into the Atlantic Ocean to sink our shipping. And they sank a lot of it. They really did. Being a merchant marine on one of these ships was, for a time, the most dangerous thing you could do in World War II. And look, I'm a Marine. I know all about taking beaches. I know all, yeah, this was still more dangerous. It just was. Let me show you a graph that I did. So the orange is Liberty ship losses, right? It's our transport losses. Okay, blue is U-boat losses. Okay, so remember, war doesn't start in 1941; it starts in 1939. Okay, so pretty low grade conflict here, right, between our transport ships and their submarines, and so not too many of either lost, right? Now remember, we entered the war in 1941, but we entered the war in December of 1941, right? So I don't know how much that really counts, right? It's not going to be until 1942 that we're really in it. And look at how many Liberty ships we lost. A touch over 500. Well, they only lost a touch under 100. Let's just round those to 100 and 500, right? So they're sinking 5 of our transport ships for every one of their submarines, and that's not going to work. That is simply not going to work. This 1942 is how you lose a war. There is no way we can sustain those losses and win the war. There's just no way. And I promise this will have something to do with plate tectonics. Bear with me. Okay, but look what happens in 1943. Our transport ship losses plummet, and their submarine losses shoot up, right? And then in 1944, they actually cross, right? We actually sink more U-boats than they do transport ships. And then by 1945, it's over. So what happened between 1942 and 1943 to turn this around? Well, when I do this in person, I always have a couple people who say sonar. Yes, sonar, right? We invented sonar, which is, one of these really weird, obscure things, right? Because what you're doing here is you're bouncing sound off of objects underwater, right? And there's always these people who like to look at, projects that the National Science Foundation funds and go, why on earth are we studying that? And you can just hear someone saying, why are we paying all this money to study bouncing sound off of things underwater? Well, here's one reason why. We'd rather not lose the war. And so this company that figured out how to do this, by the way, went from about 24 employees to about 5,000 in a week, because the Navy said, hey, we need one of these outfits on all of our ships. Every single one of them, right? And so the Navy outfits them, and so now we can detect the submarines, you can sink the submarines. Totally changes the balance of power in the naval battle in the Atlantic and the Pacific, for that matter. And so what does this have to do with plate tectonics, right? Well, Harry Hess, once he gets his sonar, he says, hey, Although I'm sure he didn't actually say that. But anyway, he says, look, if we point this thing straight down and as much as possible run it, right? What that will do is sound out the seafloor, and we'll know what the ocean floor looks like, because no one knew at this point what the ocean floor looked like. And so he goes to the Navy with this project and says, look, as we are, you know, crossing the world's oceans, if we sound them out as much as it is safe, because sonar makes noise that submarines can find, so you can't just go pinging around all the time. But anyway, as much as it's safe, if we could do this, we'll know what's down there, which is not just for science, because we've got our own submarines too, and it would be really nice not to go running into things when you're, submarining around down there. So anyway, so the Navy was like, yeah, that's a good idea. And so they did. All right, so all through World War II, as our ships were traveling, if they weren't in danger or in immediate danger, they would run these sonar rigs and sound out the seafloor. And so by the end of World War II, we had a map of the seafloor. This map was drawn from Navy data by Marie Tharp and Bruce Heason. Marie Tharp actually did most of the work, and it's only been recently that she's really gotten the credit she deserves. She was a first-rate geologist and cartographer, and she drew this map. Interestingly, Bruce Heason never believed in plate tectonics. He was always an expanding Earth guy. Marie Tharp was like, "Oh no, we're gonna move some plates around here." But anyway, so we look at this and we realize, right, that first of all, there is no mountain range connecting North America to Europe, right? Nor is there, an extinct land bridge or series of islands. No, right? Because for the longest time, people just kind of assumed that, let's say you walk off the beach in Miami, people just kind of assumed that you would just walk and walk, and the water would get deeper and deeper and deeper, and then it would get shallower and shallower and shallower until you came up over here in, I don't know, what is that, Morocco, or like, I don't know what country that is, Africa. Okay. And people, but no, right? No, right? There's a giant mountain range running down the center of all of the world's oceans. It's not just the Atlantic, right? If we come over here to the Pacific, there's a mountain range, running up through here. The deepest water is not in the middle of the ocean, but it's near the edges, right? There's some, the deepest water in the world is right there where I'm pointing. And then, but there's also deep water all up through here, down through here. The deepest point in the ocean is there. The second deepest point in the ocean, by the way, is the Puerto Rico Trench, right there. I was, on a research cruise sailing across that one time, and I was on the bridge just kind of idly watching the instruments, and suddenly I see the bottom just fall out of the depth gauge, and I looked at the captain and I said, that water's getting deep. And he's like, yeah, that's the second deepest water in the world, you didn't know that? And I'm like, no, I did not. A little bit creepy. Didn't really matter. It's not like you're going to reach the bottom here, but it was kind of interesting. So anyway, so, the shallow water isn't where people thought it would be. The deep water isn't where people would thought it would be. And then if we go back to the Pacific real quick, we can see, these, that the Hawaiian Islands actually geologically extend up here into what we call the Emperor Seamount Chain all the way to the Aleutian Trench. There's a lot of island chains. There seem to be a couple of different kinds, but there's a lot of island chains out here. And everything was just much more complicated than people really thought. It just was. And so this really caused people to take another look at the seafloor, and in the same time take another look at Alfred Wegener and his idea of plate tectonics, or rather his idea of continental drift, and let's see if we can turn it into something that works a little bit Better. Okay, let's take a break. I am about to put 5 minutes of waterfall and chimes in here. It might be a little loud. Turn it down because I use the system volume to do it, but turn it down to a nice low, dull roar, if you will. And take about 5 minutes and breathe, get up, walk around, get yourself some water, do something like that, and then be back in front in 5 minutes, and we will continue on for a little bit longer. And then, like I said, my idea is a total of about an hour to an hour and 15 minutes. Okay, so take 5 minutes and breathe and walk around a little bit. Okay, I'm back. Now, isn't that much better? Yeah. You all fast forwarded through that 5 minutes, didn't you? Nah, I know you did. Okay, anyway. Harry Hess comes back from World War II and he really starts to turn his attention to the seafloor and what was kind of going on. And in particular, I'm going to go back to this. Let me see. I'm going to go back here for a second and point out this area right here. Around Iceland, and in particular, how this mid-ocean ridge comes up and literally through Iceland. Iceland is exposed mid-ocean ridge. Iceland is seafloor that is exposed above water. It is Disneyland for geologists. We love Iceland. And so Harry starts looking at Iceland because here's the other thing. Iceland is covered in volcanoes. It is. We'll talk more about these later on, but Iceland is just covered in volcanoes. And so Harry Hess starts looking down here along the ridge to the south of Iceland, and he starts looking at heat flow. And he realizes that these ridges are hot. That these ridges are very hot, and there's something going on here. And so he gets this idea. He says, look, if we take a cut across that ridge and we kind of turn it up and look at it from the south, it looks like that, right? It looks like this, where you've got here, hold on, there's the water. Okay, I need to make it darker blue, but that's okay. So here's that ridge, and that ridge has a valley in it. I drew a valley there because there's a valley there. And Harry Hess has this idea. He says, look, I think what's going on here is that there's magma coming up underneath these ridges, and that's kind of why these ridges are there. And the reason that magma is coming up is because these slabs of rock on either side are being pulled off. Now, I said that in a very specific way, okay? Because I don't know who might have taught you this before, but you might have learned that that this magma is coming up and it's pushing on. No, it's not pushing. We know it's not pushing. And when we talk about faults, I'll show you why or how we know it's not pushing. Is not pushing. Okay, what's happening here is the rock on this side and the rock on this side are moving in opposite directions, and that is kind of creating this suction, if you will, that is pulling magmatic material up, and as it goes up, it melts and turns into magma. I'm sorry, it's pulling mantle material up. As it goes up, it's melting, turning into magma, and getting plastered on here. But this business of this magma coming up is being driven by these two slabs of rock on either side moving outward. So we want to kind of make sure we get that. There's kind of the fancy three-dimensional picture from your book showing, oceanic crust here, on this side of the valley moving this way, oceanic crust on this side of the valley. Something's in the way of my mouse here. Hold on. There we go. Oceanic crust on this side moving this way, and that's creating this suction that's drawing this mantle material here upward, and as it comes up, the pressure is released, and it goes from being solid to being liquid to being magma, right? There's this idea out there that the mantle of the earth is liquid. It's not. It's solid. It's a solid that will flow, and we'll talk more about that. But it is. But as it comes up and the pressure is released, it melts. And so, but once again, this is not pushing these plates. It's being drawn up by suction from these plates on either side, moving off, right? And so Harry has realized this. And so, he comes out with this idea that he called seafloor spreading, right? And so, with that detail from the sounding of the Navy during World War II, Harry Hess was able to figure out, or the Navy was able to figure out what the seafloor looked like, and then Harry Hess figured out the heat flow and published a paper called The Origin of Ocean Basins, laying out this idea that the seafloor is moving. Now remember, and I won't slide back on the slides, but remember that one of the big problems with plate tectonics or rather with continental drift, was that he thought that the continents were moving, but the seafloor wasn't. Well, Harry Hess comes along and says, no, no, no. Seafloor is moving too, which might make it seem to be more of a problem, but it's actually less of a problem, right? And then once you realize that the mantle of the Earth down there might be solid, but it will flow, we begin to get an inkling of a mechanism, and things just start to become much more clear. The other thing is Harry Hess is a very well-respected geologist, right? And so all the geologists were like, "Oh, Harry's got an idea. That's cool." And meanwhile, Harry's like, Wegner, So anyway, yeah. He publishes this paper, and everyone jumps on board. I mean, it was everyone's like, oh my god, this makes so much sense. This solves so many problems, and that just set off this flurry of activities. Through the 50s and 60s and 70s, even to this day, just doing all kinds of things, hauling magnetometers over the seafloor and just all kinds of stuff, working out the details of this, right? And we'll talk some more about some of those details. But if we're going to do that, we really kind of need to have a little bit better idea about the composition or the large scale structure of the earth. Now, see, there's these words that you might have heard, and we kind of need to be clear about what they mean, right? What exactly does, crust, mantle mean? And then I've got some weirder words, lithosphere and asthenosphere and things like that. And so here's the trick. If you want to talk about the structure of the earth, there's two different ways to do that. Okay, and one of them is based on composition. And the main thing that we want to track with respect to composition is silica, SiO2. And silica, this is the first time I mentioned silica in the course of this class. Let me do something fancy. Here. And so this is the first time I mentioned silica in the course of this class. But yeah, it turns out that this is going to be this chemical is going to be very, very important going forward. This is what we're going to use to classify igneous rocks. Silica determines how explosive your volcano is. It determines how quickly your rock is going to weather. It determines when your rock is going to solidify out of that magma. There's all kinds of things that are tied to this. And so, as we go along, there's 3 or 4 things in geology that you really have to understand, and silica is one of them. It absolutely is. And so we want to get that. And so when we talk about composition based, that's really what we're talking about. And so here we have the crust, right? That's this upper layer of the earth. It is generally very high in silica. Okay, and don't worry about percentages because they vary a lot. Okay, and so we don't need to worry too much about that. But generally high in silica. Now the next layer down that begins at the bottom of the crust and then goes down to the outer core is the mantle. Okay, the mantle is solid. Okay, but bits of it will flow. Maybe not the upper mantle, but most of the mantle will flow. Now, this idea of a solid that will flow, it might be a little bit weird, But I don't know. We have solids that flow, right? Play-Doh. Right, Play-Doh is a solid. If I was teaching this face-to-face, I would have probably had the presence of mind to grab my Play-Doh, because I have some. But Play-Doh is a solid, right? If I put it in a glass, it doesn't form itself to the glass. It's solid. But if I push on it, it flows. Right, well, the mantle of the earth, most of the mantle of the earth is like that. It will flow. And then below that you have the outer core that is made a lot of iron in the outer core. The outer core is liquid. And then the inner core is also very, very iron rich, and it is solid. Okay, so composition-based crust very high in silica, mantle lower in silica, and will flow. Outer core made mostly of iron and liquid. Inner core made mostly of iron and solid. There's also some radioactive elements in there that are also important that we'll talk about. Now, another way of thinking of this, though, is in terms of physical properties. Now, I already mentioned some physical properties up here, in that the outer core is liquid and the inner core is solid. But we can take that a bit further. The upper part of the mantle, despite being lower in silica, is rigid. In other words, it won't flow. That's why I kept saying most of the mantle. Okay, so there's this bit of the mantle up here that is called lithospheric mantle. It is brittle. If I hit it with a hammer, it doesn't go splat, it breaks. Okay, and so if we take the continental crust, which also doesn't go splat when you hit it with a hammer, combine that with the lithospheric mantle, which is once again brittle, this brittle layer is called the lithosphere. And so you have, the crust and the upper part of the mantle combined into something that we call the lithosphere. And you can see that the oceanic crust out here is a lot thinner than the continental crust. And for that matter, what we would call oceanic lithosphere out here is thinner than the continental lithosphere. Now, underneath that lithosphere, we have a layer called the asthenosphere, and this is solid, but it'll flow, right? It's very, very weak. It'll flow. It's almost kind of like a lubricating layer here in between the solid lithosphere and then the rest of the mantle, right? And so you got a very, very weak layer here, which it turns out is going to help us a lot to get these plates to move, because that's a tricky thing, okay? And then we've got the same mantle we were talking about before, very low in silica, solid, but will flow. The asthenosphere flows better, okay, than the normal quote-unquote mantle, and then the outer core, which is just liquid, and then the inner core, which is still solid, right? And so there's a couple of different ways. So a lot of times, geologists will use the word lithosphere, and that refers to, yes, the crust, but also the upper part of the mantle. Okay, a lot of times people use crust and lithosphere almost interchangeably. You can kind of get away with that. Don't do it in a publication, but because people are going to be, wait, do you mean, what are you talking about there? But generally, yeah, you can kind of use these interchangeably, but if you're really being precise, you need to decide which one you mean. So there's a couple of different ways of looking at this. So if we think about plates, there's a whole bunch of plates. These are the major ones. There are smaller ones. For example, the Caribbean isn't as much one plate as it is a whole bunch of microplates. The tectonics of the Caribbean are quite complicated, actually. But not every tectonic plate has a continent on it, right? For example, the Pacific plate out here, does not have a continent. The Nazca plate does not have a continent, nor does the Cocos plate, for that matter. But the South American plate does include, South America. The North American plate includes North America, but also slides all the way over here to the Kamchatka Peninsula, and then about halfway down Japan, off the coast anyway. And so, the tectonics of Japan, it turns out, are actually quite complicated too. And then, so we have these different plates. We've got a new plate kind of forming here, which we will talk about. But you can also see that that there are different kinds of boundaries between tectonic plates, right? Because here's the trick, right? It's not like these tectonic plates have, room to move without hitting each other, right? They're all bunched up right next to each other. So if they're going to move, they're going to grind, and something is going to have to give, and so plate boundaries are kind of where the where the fun is here, so to speak. You've got, for example, right here, you've got a divergent boundary where tectonic plates are moving away from each other. Over here off the west coast of South America, you have a convergent boundary, where plates are moving toward each other. And then this is not a very good example here, but in here, and also let's say up here off in California, you have a transform boundary where tectonic plates are sliding past each other. And this one really might not be clear right now, but it will be. Okay, but as I mentioned before, these plates can't just move, not without grinding against each other, right? Here's a map showing, well, the blue dots are earthquakes, and the red, are those triangles? Yeah, the red triangles are volcanoes. So we can see a really interesting pattern here, right? Wherein the earthquakes and the volcanoes usually, not always, but usually, outline tectonic plates, right? I mean, if I just kind of draw right there, I mean, if I was to give you this and say, okay, use this map to draw the tectonic plates. Well, okay, right, there's the Nazca plate, there's the Cocos plate, right? Here's the Pacific plate over here, there's the Philippine plate, here's the Scotia plate. You can even pick up the little Juan de Fuca plate there, right? I mean, you can do that. You can totally do that, right? Not all of them, right? North America is actually particularly famous for having earthquakes that are nowhere near a plate boundary. I was in one just a couple of weeks ago. I don't know if y'all remember that little earthquake in North Carolina. I felt that. It was pretty cool. But earthquake. Volcanoes kind of do the same thing. Now, Hawaii is a big exception, out in the middle of the Pacific Ocean with no plate boundary near it, and there are others like that as well. But most volcanoes occur at least near a plate boundary, right? The volcanoes here in Iceland, that's a divergent boundary. The volcanoes here in South America, that's a convergent boundary. There's another convergent, et cetera, et cetera. Right? Not all of them. Now these down here running down through western, or rather eastern Africa, are going to be particularly interesting, and we'll talk about them. But yeah, so if I look at this map of the distribution, in particular of earthquakes, and I look at this map of the plate boundaries, and the maps are kind of centered differently, so bear with me. But they kind of match up. They kind of match up, and so it would seem that the geological quote unquote fun is at these plate boundaries. And so let's think just a little bit about it. I'm not going to go too much longer. I got a timer going, I promise. But let's just think a little bit about this, okay? And so there's three kinds of plate boundary, right? If I have two plates, they can do three different things, okay? They can move away from each other, in which case we call them divergent plate boundaries. They can slide past each other, in which case we call them transform plate boundaries. Or they can move toward each other, in which case we call them convergent plate boundaries. Okay, and so there's three different kinds. Okay, and each of those is going to produce a little bit different tectonic setting. There's going to be a little bit of a different situation with earthquakes and volcanoes and whatnot at each of those places, right? And I've got pictures down here. On the left is a volcano, I want to say in Iceland. That would kind of make sense. Showing the sort of volcanism that is associated with divergent plate boundaries. This is the San Andreas Fault out in California, showing a transform boundary. And then on the right, we have a volcano in South America. Don't know the name. I can never pronounce those names. But with a lot of lightning. And that's not a Photoshop. That's real. Those volcanoes in South America are not to be messed with. They are violent volcanoes. Okay, so let's take a moment and think a little bit about divergent plate boundaries. So these are areas where tectonic plates are moving away from each other, right? And so first of all, mid-ocean ridges, right, are divergent plate boundaries, right? Those mountain ranges running down the center of all of the world's oceans are divergent plate boundaries. I've got one over here. We've seen this before, right? I've got one over here that way. That's a divergent plate boundary. Now, the fun thing about Iceland is, as we saw before, Iceland sits right on a divergent plate boundary. It is divergent plate boundary. It is seafloor that is currently exposed. Right now, I don't mean it has coral, and I mean it's geologically, rock-wise, it is seafloor. That is, like I said, currently exposed. So this side of Iceland is moving this way. This side of Iceland is moving that way. It is divergent plate boundary. And in fact, if we go there, you can see where the Rift Valley is, right? And you can see Iceland here sitting on that mid-ocean ridge, and this is moving that way, and this is moving that way, and there's the Rift Valley. It actually splits. Right there, it's kind of sorting itself out, but there's what it looks like on a map, and here's what it looks like in the world, right? This is a valley. We're looking north here, and so over here is geologically, Europe and Asia, and over here is geologically North America, and so this is moving that way, this is moving that way. They call this uplifted rock. That is uplifted only relative to this rock, and so, we'll talk a little bit more about this faulting and kind of how we know some things. Based on this, and so, oh, I'm sorry, I got that wrong. We're looking south. That's the North American plate there. Okay, sorry, didn't notice that. So, but regardless of which plate it is and which direction we're looking, this is moving that way, and this is moving that way. And there are places where you can go scuba diving in between the two tectonic plates. And let me tell you, buddy, if I ever get to Iceland, I am doing that. And so I've been scuba diving all kinds of places, but I've never been scuba diving between two tectonic plates. So I can guarantee you I am doing that, and someone is taking a picture. So anyway, so this idea of divergent boundaries actually brings us to a volcano that had this ridiculously unpronounceable, well, not ridiculously, this absolutely unpronounceable Icelandic name. And there it is. Feel free to try to pronounce that. I had a friend who actually studied this volcano, and she spent an entire afternoon trying to teach me how to say that, and it never worked. So I just call it Bob. And Bob erupted in 2010 and spewed all kinds of ash into the air. I mean, it was amazing. The ash this volcano put into the air. But the fun thing about Icelandic volcanoes is that ash actually blows away from Iceland pretty quickly. This Bob here is kind of on the south side of Iceland, and the ash got blown to the south, actually to the southeast, over Europe. And I don't know if y'all remember or not, but this thing shut down air travel all over Europe for, I don't know, a couple of weeks, because you cannot fly your airplane through volcanic ash. Jet engines are actually hot enough to melt this, but then it sticks to the engine parts, and so basically what you end up with is a jet engine full of igneous rock, and that is, as they say, a bad way to fly. And so, it didn't bother Iceland that much, but absolutely bothered Europe. And actually, Icelandic volcanoes have a long and proud history of erupting in Iceland, but messing with mainland Europe. This volcano doesn't look like much. Sorry, I don't have the plague. My throat is dying from talking. Fortunately, I'm almost done. Anyway, this volcano, Laki, erupted between 1783 and 1784, threw a whole bunch of sulfur dioxide into the air, killed half of the livestock and a quarter of the people on Iceland, probably from starvation because it killed their livestock. Just absolutely horrible volcano. But also spewed out a whole bunch of ash, a whole bunch of sulfur dioxide, all kinds of things, and caused crop failures all over Europe. All over Europe. Now, I don't know if you're enough of a history person to know what was going on, particularly in France in the late 1700s, but the French Revolution, right? Basically, a whole bunch of hungry French people got pissed off and started lopping the heads off of their kings and queens and whatnot. And yeah, French Revolution, caused by a volcano. That one, okay, not really caused by a volcano, but a volcano definitely came into play. People don't like being hungry, they really don't, and that volcano caused famines all across Europe. And so it most definitely was a problem. And so I tell you what, I am going to stop with this lecture here. I might be a wee bit early. I don't know. I had my alarm set for 30 minutes. I'm at 25, but that's probably good. So we're going to pick up here with continental rifting, which next time will also explain why you get these volcanoes in eastern Africa of all places. And so we'll talk about that. And then we're also going to talk a little bit about humanity, because this area of Eastern Africa is where humanity comes from. So it's a fascinating, fascinating place. So come back for the next lecture then. I'm going to go ahead and shut this one down and get it uploaded and get it out to you guys. So come back for another lecture. And actually, well, never mind. I'll talk about that later. Okay, bye-bye.